Hello once again. This is something we haven't seen in many years on my videos. It's my Newmar 12 volt linear power supply. This is a 2 amp 12 volt linear power supply given to me by my late grandfather many years ago. And this thing was a mainstay in my earlier videos in years past. I always use this in my videos to power anything that needed 12 volts. But a few years ago, it suddenly stopped working. It doesn't put out any voltage anymore. It's not the fuse. You put a multimeter to it, and when you turn it on, it slowly climbs up to like 5 volts, and it stops there. And I've had this thing apart a few times since then to try and figure out what's wrong. It's got a transistor right here. I tested that a couple of years ago, and it tested okay. But a linear power supply is so simple. I should be able to figure out what's going on with this thing. So in today's video, we're going to take this thing apart yet again and see if we can figure out what's wrong with it, see if we can fix it. Model 115-12-6, the 12 means 12 volts, and I believe the 6 means 6 amp surge. It's got a serial number on it, very low serial number. This is a commercial grade marine power supply. This was meant for a marine application for powering, say, marine VHF radios. But this is a commercial grade heavy duty power supply. It's very heavy. Of course, it's a linear power supply, so it's got a big transformer in there that makes up the bulk of the weight. And it has 2 huge filter capacitors in the massive capacitors, several thousand microfarad. This plug I put on it, the original plug had the ground pin broken off it. Very common thing among my family. My family all seem to live in houses that don't have grounded outlets. They're so old they don't have the ground hole in them, so they have to break the ground pin off so they can plug it in. So when I got this thing, I put this new grounded plug on it. And this cap pops off. And under there is the transistor. Look at that, a big TO3 package transistor, RCA transistor. And I just noticing now, I wonder if that's a date code, 7917, 17th week of 79? I've never known how old this thing is. I didn't think it was that old, but I suppose it could be. So let's take this thing apart and see what we find inside. To get this apart, there's 2 screws on this side and 2 on this side, and I think I just unscrew those and this top plate comes off. So I'll see if I can do that and we'll come back. Okay, so I actually got a bit backwards. The unit's upside down now and the bottom piece actually comes off, and that has all the controls on that piece, and then the output actually stays on the other piece. But yeah, it's fairly simple. There's actually a bit more circuitry here than I remember, and I suppose that's why I didn't get very far in testing it. You can see there's a few components there. Just by the look of the circuit board, I can see those are probably hand-drawn traces. Yeah, I guess I can believe that this thing would be from 1979 now that I look at it. But how it works is you got your AC coming in there, and the green wire is ground, and that looks to go... Ground actually goes to the frame of the transformer, fair enough. Or one of the brackets mounting the transformer, so that makes sense. So the whole case is grounded. And phase goes through the fuse into the switch, and the other end of the switch goes into one of the legs of the input side of the transformer. And then neutral goes into the other leg of the input side of the transformer. And then there's actually 3 legs coming out of the output of the transformer, which is what makes me worried, because that means there's some sort of feedback circuitry happening or something like that, or maybe it's just center tapped. I don't know. I'll have to take a closer look at it. But if we lift this up, there you can see the 2 big DC filter caps. This thing's old enough that it uses MFG for microfarad. 5100 microfarad, and these are old enough that it uses MF for microfarad. 5100, 25 volts. These are paralleled. So there's a total of 10,200 microfarads, 10.2 millifarads for filtering. Wowee, but that's how a linear power supply does. And, oh, that yellow capacitor, 0.1. Could that be a paper capacitor? Maybe I should just recap this thing. If this thing's as old as I think it is, maybe I should just buy new caps for it and recap the whole thing. Because this thing has turned out to be way older than I thought it was. That cap says Delco on it. 100 microfarad. So this yellow and green striped wire, that's the center tap, I think, just going by the physical placement of the transformer. And that's going into the positive. So this is the positive 12 volt rail. So that yellow and green wire goes right to the positive. So that makes... Well, it doesn't make sense, because where's the regulator? Because there's that big fat transformer, or transistor there. That would be part of a regulator circuit, I assume. Ah, I see an IC over there. So that might actually be the regulator. I don't know. I'm going to have to see if I can get this board out of here so I can analyze it a bit further. But it's a good start anyhow. Okay, so I've spent some time going over the circuit, which as you can see I've removed from the casing and the transformer. And I've made a little bit of sense of it, but there's still some parts that I don't quite get. I had a hard time figuring out what the heck these two components were. I didn't know if they were a weird inductor or what, but then I looked closer at them and I saw that they have a little diode symbol on them. So these are diodes. They are the rectifier. Beefy diodes, I found the data sheet online. Each diode's rated for like, I think 6 amps continuous and like 20 amps surge or something like that. Pretty good. So this rail is the DC ground, and this is the positive DC rail, filtered but before regulation. And I'll give you another look at those capacitors. Made by Mallory, kind of cool. There are some vintage electronics enthusiasts that when they encounter capacitors like these that aren't in the best of health, rather than just replace them, they'll actually go through the effort to try and nurse them back to health just by running voltage through them until they start coming back. The ESR lowers and stuff like that. It's kind of cool. Very big capacitors, 25 volt rated. So then after that is where I get a bit confused, because there's all this circuitry here and I found that there's actually two 3-pin ICs. This one over here is actually the regulator. It's a 7912 regulator. It's just a normal 12 volt linear regulator. And here's what confuses me. It's only rated 1.5 amps according to the data sheet. But the other IC, I've cleaned it, but I can't make out all the numbers on it and what numbers I have made out. I look it up and I can't find anything. So there's this component, and all I can make out on the bottom, it looks like it says H310 and then another character. I don't know if it's a P or an F. And then I can't make out what's on the top. So I have no idea what this is. And I haven't dug into the circuitry layout yet to try and figure out what it is. And the problem is, another thing I've just realized is it almost looks to me like the DC end of things is positive grounded. Because once you have these rails here, the final positive output is connected right to the positive rail before the regulation. So the regulation seems to happen on the negative side, which is confusing. Not the way you do things today anyways. So it seems to me like all the regulation might be done on the negative side, which means the circuit is wired such that rather than this being 0 volts and this being 12 volts, this is 0 volts and this is negative 12 volts. So it's very interesting. And like, of course, the IC that I've been able to identify, that's just a normal linear voltage regulator, I try to trace what it's doing on the circuit, and I can't make a whole lot of sense of that. There's like a resistor tied to the ground point, and the output goes to the negative DC output, which is what makes me wonder that this thing's positive grounded. It's very, very strange. And so that left me wondering, what the hell is the transistor for? And all the other circuitry. And I went on Newmar's website, and they don't have a manual or a schematic for this because this is way too old. But they today sell a power supply called the 115-12-8. This is the -6. Today they sell what's called the -8, and it looks almost identical, but it's rated a bit higher. It's rated for 8 amps surge and I think 5 amps continuous. And in the manual for that, they have basically a block diagram of how it operates. And from what I gather, the other circuitry I've yet to identify on here is actually for over voltage protection. If something goes wrong with the regulation and the regulation breaks, the circuitry on here shuts things down, quenches any extra voltage to protect the load from voltage spikes or whatever. So that makes sense. But yeah, now I'm just going to see if I can figure out how these ICs are tied together. And I don't know if I'm going to be able to find what this IC is, and just see if I can figure out what might be going wrong. We might get to a point where what I'm going to have to do is just plug the thing in with it apart, which I'm not going to like doing because I don't like working on 120 volt stuff when it's live, although I've done it before. But I might have to plug this in, turn it on, and just start probing things. Make sure the output of the transformer is good, probe the DC rails here, make sure I'm getting a reasonable DC voltage, 15, 20, 25 volts or whatever. And then just start probing around until I find the point where things stop working. Well, it is 3 months later. I filmed the previous parts of this video in August and just totally dropped the ball for a long time, moved on to other things, and totally forgot about this thing, left it disassembled even, and I'm lucky I didn't lose any screws or anything. But check this out. It lives again. Oh, it's fantastic. I have fixed this thing. The voltage regulator blew. That 7912 voltage regulator. I bought a new one on DigiKey for like $1.72. Put it in an order with a bunch of capacitors I bought for other things. Soldered it in and it works perfectly. This power supply is revived and I am so happy. So how I diagnosed and determined that the voltage regulator went bad was I basically powered the unit on while it was disassembled, and I basically took a multimeter and I measured the voltage at the capacitor, so the output voltage before regulation, and I got an expected value. I don't remember, but it would have been like 20 volts DC or something like that. And then I measured the voltage directly at the output of the voltage regulator, and I got basically nothing. I got a very erroneous value, and so what I did was I desoldered the voltage regulator because it's a linear voltage regulator, and linear voltage regulators are nice for troubleshooting because you don't need any external componentry to test them. You can literally just take the regulator chip by itself, hook up power to it, put a multimeter or a load or whatever on the output, and see what you get. And what I got was, when the voltage regulator was removed from the circuit, was that open circuit, it was outputting perfect voltage, exactly as it's supposed to, but as soon as you put the slightest load on it, the voltage went down to 0. And so that's how I determined that the voltage regulator was bad. So there were a lot of things, things that confused me, a lot of misconceptions and and incorrect assumptions I made about the design of this power supply while I had it open and was looking around at it, that I was able to clear up as I dug into it further and ultimately desoldered the voltage regulator. First of all, I was confused as to why the output of the transformer was center tapped, or at the very least it had 3 leads on it. At first I thought that 2 of the leads were going to the same place. They just had 2 leads in one spot for some reason. And in addition to that, I noticed there were only 2 diodes on the circuit board, and so I thought this thing had a half-wave rectifier, which was very confusing to me that such a high-quality, heavy-duty power supply would have only a half-wave rectifier instead of a full-wave rectifier. Well, first of all, I completely forgot that you only need 1 diode for a half-wave rectifier, not 2, so that was derp on my part. But I did some reading, and what I discovered was when you have a transformer that's center tapped at the output, you only need 2 diodes to get full wave rectification, because the diodes are common to the center tap, and then each diode, the other end of each diode, goes to the end tap. So I have a little diagram here I found on the internet I'll put up. So yeah, when you have a center tap transformer, you only need 2 diodes and you get full wave rectification. So that's one thing about this thing's design that I cleared up. The second thing I found was that you may have heard earlier in the video that it had seemed to me that the design of the power supply was, I called it positive grounded. Well, that's not really correct because this is an isolated power supply. There is no common ground. But positive referenced. It had seemed to me that the power supply was positive referenced, meaning that at the output, rather than negative being 0 and positive being plus 12, positive is actually 0 and negative is minus 12. So from the end user, it doesn't seem any different. It's negative and positive, but from the standpoint of the actual circuitry, it's working quite a bit different from what the layman would expect. And I turned out to be correct on that. This is a positive referenced power supply. What I didn't realize though is that the 7912 voltage regulator, that's a negative voltage regulator. So rather than the output being negative referenced and the output being 12 volts, as what you'd find on the 7812, which is a common 12 volt linear voltage regulator, on the 7912, it's the negative complement of that, or the inverse complement, if you will. So the ground point of the regulator is the positive, and the output is negative 12 volts. I have no freaking clue why somebody would design a power supply around a positive referenced output. If somebody can educate me on that as to why they did it this way instead of a normal negative referenced design, by all means, I'd love to know, but it was very interesting to me to find out that this indeed uses a positive referenced output. So that was that cleared up. And then there was that other IC, that 3-leg IC that I had no idea what it was. I posted a picture of it on a vintage electronics group that I'm on Facebook. It's called Vintage Electronics Collectors, and asked, what the heck is this? Because obviously the print on that IC is not very readable anymore. And I basically got 2 answers. Some people said that it was a Hitachi K310 silicon controlled rectifier or thyristor, and other people said that it was a 2SD212 NPN transistor. 2 different answers, no idea which one is correct, but it is evidently one of those 2 things. What can be said for sure, though, that it is part of the circuitry that serves as the overvoltage protection. So this thing has overvoltage protection. If the circuitry fails in such a way that the output rises significantly above 12 volts, that circuitry activates and it basically shunts out the output. So whatever you have connected to it is not damaged by the excessive voltage. Another thing I was confused about is that this thing is rated for 6 amp surge. The model name or model number 115-12-6. 115 is the input voltage, 12 is the output voltage, and 6 is the output surge current rating. I found it very odd that this is rated 6 amp surge, but the voltage regulator is only rated for 1.5 amps. And I thought, well, how could that be that, and the voltage regulator doesn't even have a heatsink on it, and it's a linear regulator, so the thing's going to be putting off a significant amount of heat with any sizable load on it. So I thought, how are they doing that? Well, then it occurred to me, I forgot all about this big transistor here. This is an RCA 2N3773 NPN, I believe, transistor. And I don't know how exactly it works, but from what I gather is actually happening is that the actual voltage regulator is generating the reference voltage to be output, but then this transistor is actually handling the output. So I think of it as sort of the regulator is saying output this voltage, and then the transistor is actually serving to help do that and handle the actual load current. So while the regulator is only rated 1.5 amps, this transistor, per the datasheet, is rated for 8 amps collector current. So very beefy transistor. It does get warm when you have a significant load on it. So this is actually handling the brunt of the load, not the voltage regulator. So I find that quite interesting. It's too bad I can't find a schematic for this thing. I'd really like to find out what all is going on and how this transistor actually interfaces with the voltage regulator. I suppose it's probably some sort of standard circuit. If I dig around enough, I could probably find something else and learn from that. And then the last thing that I sort of learned about this thing just by looking at it more, well, actually, this was obvious. It was, even earlier in this video, you can see it plain as day, but I didn't even realize it until literally just recently after I fixed this thing. I sort of looked at it and I was like, oh, duh. I've always considered this to be rated 2 amps continuous and 6 amps surge. Well, my only reference for that is this fuse, which is rated 2 amps, but this fuse isn't on the output, it's on the input, it's on the 120 volt side of things. So this thing isn't rated 2 amps continuous, it's rated far more than that. And I did some back of the envelope calculations. I basically measured, considering the power factor, what the power consumption of this thing would be with a full 2 amps on the input, factored in the efficiency of it, and basically did the calculations to gather what the maximum continuous output current would be. And based on my calculations, this thing should be able to handle 4 or 5 amps continuous on the output, which is far more impressive than I ever thought. I always thought 2 amps was a little odd for how, big and heavy this thing is, although it's a linear power supply, so it's going to be big and heavy. But yeah, it turns out this isn't a 2 amps power supply. It's, based on my calculations, 4 or 5 amps continuous and 6 amps surge. At least that's how Newmar's power supplies today are labeled. The last number in the model is the surge current. But maybe when they made this one, it was the continuous current rating. So maybe this is rated for 6 amps continuous. I don't know. But I'm pretty confident now with my calculations that this thing could handle at least 4 amps continuous at the output. So I'll consider it that. I'll just use 4 amps as a personal limit for how much of a load I can put on this thing. And yeah, this thing's even beefier than I thought. Which makes it all the more odd to me that the voltage regulator blew in the first place, because the voltage regulator blew when I was trying to run the Browning portal lamp on this thing. The Browning portal lamp consumes about 1.5 amps continuous, and about 3 amps surge for the first couple of seconds when you're preheating the lamp. So I find it all the more odd that the Browning portal lamp was what this was powering when the voltage regulator blew. But the Browning portal lamp is a vibrator power supply, which generates a ton of switching noise, basically, at the power source. But still, this thing has massive filtering capacitors on it, so I find it odd that the switching noise and the spiking generated by the vibrator power supply would blow the regulator. Maybe the regulator just said it was time to go and gave up. Or maybe the electrical irregularities caused by the Browning portal amp was just, made it past the filtering capacitors and was just too hard for it to handle. Although, remember, this transistor is what handles the brunt of the load, and it survived perfectly fine. So maybe all in all, maybe it was just the voltage regulator just decided to give up the ghost. I don't know. But nevertheless, I've actually been experimenting with the Browning portal amp recently. I've been experimenting with putting a snubbing capacitor across the primary side of the ballast to help quench the spikes and irregularities caused by the vibrator. And it seems to be working pretty well. I've had the oscilloscope on it, and the capacitor across it really seems to help it a lot. So I think, maybe, fingers crossed, I can try running the Browning portal amp on this thing again, and hopefully it won't blow this time. But we'll find out, I guess. And if it does blow the voltage regulator again, well, another $1.72, I'll buy another one, whatever. Speaking of oscilloscope and waveforms, I measured the voltage output of this on my oscilloscope to see what the ripple was. I had this 25-watt incandescent marine navigation lamp as the load, so about a 2 amp load on the output. And the voltage regulation and the cleanliness of the output was impeccable. This thing holds the voltage perfectly well. Open circuit output voltage is 13.3 volts, and it dipped a negligible amount under this load, so that's just excellent. And voltage ripple, 60 hertz ripple, was only 15 millivolts. That's just fantastic. And that's why linear power supplies are so great. That's why they're preferred for sensitive equipment like radio equipment and audio equipment, is because a modern switching power supply, you would start to get switching noise and a lot more ripple the more load you put on it. So yeah, this thing's just fantastic. So I questioned, whether I should recap the thing. I'm not going to bother. It's running perfectly. The regulation's excellent. The ripple is excellent. This thing is running, as far as I'm concerned, good as new. So I don't see any reason to recap it. If I ever do recap it, I'll just recap the small capacitors. I won't redo the filtering capacitors. Those massive Mallory filtering capacitors are definitely doing their job based on how well filtered the output is. So if I ever do a recap, it'll just be the little capacitors, like that weird yellow one. I'm almost wondering if that's a paper capacitor. If it is, I definitely want to replace that one. And the other couple of small electrolytics that are on there, I'll do those. But as far as those Mallory filtering capacitors are concerned, I'm not worried about those at all. They seem to be in perfect health. Alright, I'm just going to YOLO this thing and hopefully it works. Alright, the one negative side effect of having the snubbing capacitor there is that the lamp is a little harder to start because there are no longer the inductive spikes that a magnetic ballast normally uses to aid in starting the lamp. Or they're still there, but they're very much reduced now because of that capacitor. Well, it's working. The power supply's alive and the lamp is working, so I call that quite the win. Alright, that is the diagnosis and repair of my Newmar Model 115-12-6 12-volt linear power supply from 1979. I love this thing. This is one of those things where I'm just never going to get rid of this. Linear power supplies are just a treat for any person who works with electrical stuff. They're a really valuable tool. Just because they're generally just so reliable and clean and just really beefy. They can take a lot of abuse and just keep on running unless a voltage regulator just gives up for no reason. But yeah, this thing's really special to me. This was given to me by my late grandfather. Oh gosh, it was almost 10 years ago now. He was a retired fisherman, and he gave this to me with a couple of VHF radios one or both of which might have been used with this power supply. It's kind of funny and kind of confusing if you're not familiar with boating and stuff, but the primary suggested application for a power supply like this is to actually for use on boats. So the boat will have an onboard 120 volt generator, but then you'll plug something like this into a 120 volt outlet on your boat, so you have 12 volts available. Now that sounds kind of backwards. You would think the boat's engine or generator or whatever would generate 12 volts DC already. Why would you need one of these? Well, you do get 12 volts DC usually on a boat, but on large vessels running 12 volt wires all over the place that could be subject to high current, it's just not very efficient to do, because you need really thick wires to handle the current and all that sort of stuff. If you just take the 120 volts, where you don't need as thick of a wiring, and put 120 volt outlets all over the vessel, and then use one of these to get 12 volts DC whenever you need it, then you're good to go. And these would be used to power communications equipment like VHF radios, radar systems, GPS systems, you know, basically any device on a marine vessel that needs 12 volts DC. You'd use something like this, and that's the primary application that Newmar's linear power supplies are meant for. But otherwise, a power supply like this, they're very well loved in like the amateur radio community. Absolutely, a linear power supply is really important over a switching power supply for an amateur radio transceiver, or CB enthusiasts, CB radios, absolutely. Although they don't need as much power. And audio enthusiasts really appreciate a linear power supply, because the output is so clean that audiophiles really want that clean output to reduce the noise in the audio output of their equipment as much as possible. And actually, I read once on an online forum where somebody was looking for recommendations for a 12 volt power supply, and somebody said, get a Newmar, because they're pretty much the best you can get. That's what that one person said. And you know, as far as I can find, Newmar is a premium quality power supply. They're very expensive. A small unit like this one, new, is around $300. Even on the used market, one like this, 40 years old, can still go for upwards of $100. So these aren't cheap. They're very valuable devices, and for very good reason. So I'm really glad that I got this one running again. I finally revived it after being benched for 2 or 3 years, and I'm just overjoyed. This thing's going to get a lot more use now. Now that it's running, I won't have to use my jumper pack as much anymore and wear out the battery on that. So there you go. Thank you so much for watching, and I'll see you in the next video.